Okay, welcome to lab. So again, like we said before, we're going to pick up here where we left off in lecture. So right here, and probably hopefully knock out the rest of this chapter. And again, just to kind of keep us on pace and everything, since we are getting to the end. We don't want to crush everything in one day. Like usual, if you do have questions, feel free to ask them, and obviously we'll get those answered for you. And we're going to kind of move into coordination compounds and a little bit of talk about sort of complex ions. We're going to talk about how to name these guys, do oxidation states, and some other sort of situations with our coordination compounds. All right, so let us start with the idea of sort of coordination compounds. A coordination compounds usually consists of basically two things. It consists of basically a complex ion and a counter ion. So a complex ion we've seen a couple of times before. Again, that complex ion is our positive ion, as we were just talking about earlier and other times, that basically has a number of ligands that are attached to it. And as we mentioned, again, the ligands are our Lewis bases. And when you take a complex ion, it typically will have a charge. Now, much like an ionic compound, you could almost think of a coordination compound as very similar to an ionic compound. In an ionic compound, there's a positive ion, right? And there's a negative ion. And in a coordination compound, there's a positive ion and a negative ion. And the other part of that is the counter ion. So the counter ion acts really to balance out the charge. So much like when we do an ionic compound and we write the formula for it, it is always sort of neutral. Typically speaking, when we do a coordination compound, it is also neutral as well. So we have a complex ion and we have a counter ion. One's going to be positive and one's going to be negative. And again, they're going to balance each other out to give kind of no charge overall. Again, just like an ionic compound. So a couple things to keep in mind, though, is again, the two parts of it is a complex ion and a counter ion. And in certain cases, the complex ion may be positive and the counter ion may be negative to balance it out. And vice versa. You can have a negative complex ion and you can have a positive counter ion. So again, for lack of a better analogy, sort of the counter ion is almost like a spectator ion. It's kind of there to balance out the charge of everything. While a lot of times we do focus in more on the complex ion part of it, it is usually there again just to balance it out. So a reminder again that a complex ion is an ion where we have a central metal. And again, sometimes these metals are small, have a good positive charge, +2, +3s. And then again, they're bonded to one or more molecules or ions. These molecules or ions, again, are what are referred to as ligands. And ligands are Lewis bases. So those Lewis bases can donate a pair of electrons. And that's why when we look at these, some good examples here of Lewis bases or ligands, we have our electron pairs on our oxygen and water, on our nitrogen. Obviously, something with a negative charge has gained electrons, so it's got electrons to give. So typically when we talk about something being a Lewis base or a good ligand, it typically will need to have those non-bonding electrons or those lone pairs on the atom. And usually, typically, being polar and that separation of charge, sort of a positive side, negative side, helps sort of aid that process of it being able to donate those pair of electrons. So as you perhaps should hopefully know, right, water is polar, right? More negative on the oxygen side, more positive. Same thing here with our NH3, right? Dipole moment happening in that direction. Again, nitrogen being more negative, the hydrogen being more positive. So again, these lone pairs that are there usually need something like it being a polar molecule to make it sort of pretty efficient as being a ligand. Again, as I mentioned before, the chloride there obviously is an ion. It has a charge, has a negative charge, which means it has extra electrons. So again, those extra electrons are going to be able to be donated. So when we look at this here, the cobalt in the middle is our metal. This is our complex ion. The nitrogen here is what's connecting. Again, those lone pairs on the nitrogen are going to basically be shared or donated. And again, these are our chlorides, right, which has those electrons as well. And again, they're able to sort of donate those guys in. Now, when we talk about sort of ligands and complex ions, there's a couple of things to sort of keep in mind when we look at them here. And we should go back and look at it. When we talk about an important aspect, sort of a complex ion, is what is known as the coordination number. And the coordination number, and I think we might have touched upon it very briefly when we were doing KF and all that kind of stuff. But the coordination number is basically the number of atoms that are directly attached to the metal in a complex ion. And those are our ligands that are going to be attached. So for example, when water, or the NH3 that we see here on the screen, when they attach to the metal, it is basically, for every water attaches, it is the oxygen that goes and basically attaches to the metal. And same thing here with our nitrogen and NH3. It is that nitrogen atom that basically will go and attach to the metal in that case. So not all ligands, for example, will attach in just one spot, but there are a number of them that do. So water, NH3, Cl minus, these are all what are referred to as being monodentate, or sometimes they're referred to as unidentate. But monodentate basically means one, right? Mono. And that basically means that for every molecule or ion that you have binding to the metal, only one of those atoms will bind directly to it. So it's sort of a one-to-one relationship. So if we go back and look at our guy here, the Cl minus is monodentate. So we have 1, 2, 3, 4, 5, and 6 atoms directly bonded, as NH3 is also monodentate. And that means if you were going to figure out the coordination number for this guy, the coordination number here would be 6 in this case. Again, each of those ligands, the NH3 and the Cl minus, they only attach with one atom per molecule or ion. And that gives us a grand total in terms of the coordination number of it being 6. Now, as we sort of talked about a little bit before as well, not all ligands will attach in just one place. There are some ligands that can attach in multiple places per molecule that goes there. One example of that is ethyl endyl diamine. And in sort of complex ions, this oftentimes is abbreviated with EN. So you'll oftentimes see this EN sort of abbreviation, and that stands for ethyl endyl diamine. And you'll actually see that EN abbreviation both in names, and you'll also see it in formulas as well. So again, if you see that, it represents this. And what that looks like, by the way, is, something like this, perhaps. Give it the old college try here. Now, this is basically one molecule of EN, or ethyl endyl diamine. So when it attaches to a metal, in this case, the nitrogen on this end will attach, and in the same molecule, the nitrogen on the other end will attach, which means for every EN molecule that attaches to a metal, you're actually getting like a 2-for-1 deal there. You're getting 2 per molecule, which means if we had, and I won't draw it out since I'm running out of a little bit of room here, but if we added in another EN, I'll just write EN here so it's at the bottom of the screen, the coordination number here would actually be 4, even though you only have 2 molecules of EN attaching, because each of them can attach by the nitrogen, not in one place, but I'll just draw the second line, in 2 places. So basically you have 1, 2, 3, 4 atoms, and they're all the nitrogen in this case that are attaching. And again, even though you have 2 of those molecules, the coordination number will actually be 4 because it's bidentate. And another very common one that you come across that we'll see a lot in terms of bidentate is oxalate. And I think that might have been the one I used earlier on as an example. If you draw oxalate, looks something like this. That's C2O42 minus. So when one molecule of oxalate goes to bind in, oxygen here and oxygen here are going to bind. So again, if you happen to have had 2 oxalates binding in, 2 molecules of oxalate, this guy would also bind in here, and you would then have 1, 2, 3, and 4 atoms directly binding to the metal. The coordination number here would be 4 as well. So I say this that you do need to be able to recognize some of these monodentate, bidentate, and we'll see a little table. And I believe there's a table in your book as well, but we'll see some tables here in just a second. But it's important to know these ligands, and more importantly to know how many times per molecular ion are they actually binding in. EDTA is a polydentate ligand. It could actually bind like 6 times per molecule. So EDTA is a great metal chelator, as we'll talk about. It's able to basically snatch up a metal and basically surround it in 6 different locations on one EDTA molecule. So monodentate, bidentate, and again, polydentate. When you look at a formula, it may not always be the subscript as to the coordination number, again, depending on whether it's mono or bidentate or polydentate. So you may ask, like, how do I know how many ligands would bind into a metal, for example, And there's sort of a general rule, and these are some common ones. So usually, there's always exceptions. But if you have something like over here, where you have kind of a +1 charge, you can see that very commonly the coordination number typically will be 2, occasionally 4 as well, but mostly 2s and 4s. If you have a metal that has a +2 charge, you can see that a lot of the common coordination numbers that we see are 4s and 6s. And if you have something with a +3 charge, you can see you could get some of those big coordination numbers of 6 going down as well. Gold typically, though, will go more with 4, where it's a +3 charge. So again, not 100% perfect in every situation, but these are sort of the general trends that we see in terms of how many ligands will come in terms of the charge. So you can also see as the charge increases, it's able to kind of bring in and attract those electrons coming in from the Lewis bases and allow more atoms to basically bond in. So there's ethylenediamine, which is that EN that I drew before. And again, you can see at each of those nitrogens, it's able to bind in. This over here is EDTA. And you can see from this picture, it surrounds that lead. This is all one molecule of EDTA. This is our 1 spot, 2 spots, 3 spots, 4 spots, 5 spots, and 6 spots in this one EDTA molecule that basically is able to surround that metal. and it does a really good job. And again, these guys are sometimes referred to bidentate or polydentate ligands as chelating agents, which means they basically will grab up metals and surround them very, very much. If you look at a lot of labels on things, maybe shampoos, other type of products and stuff like that, you'll sometimes see this name in it in like the ingredient part. And again, it's used a lot to sort of grab out a lot of metals and stuff like that and sort of trap them. Here's a table, again, not from your book, but I believe you do have a similar table, but here it is anyway, so you can see it. Here's a list of some of our monodentate ligands. So we got our water, our cyanide, our thiocyanate, any of the halogens, fluorine, chlorine, bromine, nitrite, hydroxide, NH3. Here again are a couple of very common bidentate ligands. So we have our oxalate, again, at each of the oxygens is going to be able to attach. And here at each of the nitrogens in our EN, it will be able to attach to the metal. This is diethyl entramine, and this is a diene. This guy could actually attach 3 per molecule, 1, 2, and 3. So if you had 2 of those dienes, you would have a coordination number of 6. If you had 1, you'd have a coordination number of 3, but you probably would have 2. And there's ethyl endyl diamine tetraacetate, or tetraacetic acid, sometimes called, and that's our EDTA. And you can see again at those 6 spots where I circled in the last slide, 1, 2, 3, 4, 5, and 6. You can also see it has a -1, -1, -1, and -1, so like a -4 charge overall on EDTA that happens there at those oxygens. So obviously these guys very, very good at basically surrounding metals and kind of trapping them in there. You should be familiar with these. Again, like I said, I'm not sure structure necessarily is that necessary to draw. Clearly, you don't need to draw EDTA, but you do need to know for these things. Like I said, the important part is the type it is it monodentate, bidentate, polydentate? How many times is it able to attach so you can correctly identify coordination numbers and so forth. And you might not have to obviously draw them per se. All right. So why don't you take a moment here and let's figure out the oxidation state of the metal. And by the way, when we do look at something written like this, this is a coordination compound. And typically speaking, when they write it like this, people will put the complex ion part in these brackets. And then outside of the bracket is typically your counter ion. So again, it could be on the right-hand side, or it may be on the left-hand side. And it's usually not in parentheses or anything like that, but I'll just put in parentheses for now. But usually when you see those brackets, that's the complex ion part. And so in this case, we're looking for what is the oxidation state of the gold in the first one and the chromium in the second one. And while we're at it, why don't you figure out the coordination number for each of these guys? So figure out the oxidation state of each of those metals, the gold and the chromium, and then figure out the coordination number for the complex ions. And we'll see how you do. So take a moment or two to do that. Okay, so let us take a look here and see what we got going on. So we want the oxidation numbers each of these guys. So as I mentioned before, when our coordination compound is written, typically in the brackets there is our complex ion part. So when we look at this complex ion, we have gold, which we may not be sure what the charge is, but we do have OH, which we should know is -1. And there are 4 of them, which gives us a -4 overall. We're looking for this guy. What we know about potassium on the outside here, this is going to be then our counter ion. And what we know about potassium is +1. So we basically got -4 and +1 is -3. That tells us that the gold here must have an oxidation state of +3. Any questions on that? Now, when we look at it in terms of coordination number, we want to look at our complex ion. Hydroxide is monodentate, and there's 4 of them attached. The coordination number here would be 4 in this particular case. Again, each of those OHs are going to attach 1 atom each, gives you 4 total for a coordination number of 4. We also, if we want to kind of delve into this, our counter ion is +1. If we add up just our complex ion part, so if we just take the complex ion part of it, we now know that the gold is 3. This guy is -1, which gives you -4. That means overall, the complex ion part here has an overall charge of -1. And like I said before, these guys are pretty much like ionic compounds. And in ionic compounds, when we write formulas, when we write names, it's always the positive guy first and the negative guy. And it's always going to balance out to 0. And it does here with our coordination compound. +1 overall, -1 overall gets us to the overall equation that we had up here, which is no charge. Any questions on that part of it? Now, if we look at our second guy here, which is this. So again, this part here is going to be our complex ion. And this is going to be our counter ion. So if we pull it down here, looking at our NH3, it is 0. It's neutral. NO3 is NO3 minus, which is nitrate. That's -1. There's 3 of them, which gives you a -3 overall. That means in this case, the chromium has to be +3 as well. So the oxidation state of chromium will be +3 in this case. If we look at the coordination number, we have 6 ammonias attached to the metal. And the 6 ammonias attached to the metal, each of them are going to attach in one spot, which would give us a coordination number of 6 in this case. I'll answer your question in 1 second on the coordination number just to make sure. And again, if we sort of break it up here, if we look at just the complex ion part, the chromium is +3. The NH3 is 0, which means the actual ion part, the complex ion, has an overall charge of +3. And that's why when we look at our counter ion, which is nitrate, we don't have just one of them, but we have 3 of them. which gives you 1, 2, 3 for a grand total of -3 and +3. So when we put them together, again, just like a normal ionic compound, it equals 0. So this is our complex ion. And these are our counter ion, really. In this particular case. All right, so I'll get to your question here in just 1 second. But first off, a couple of things to note is when we look at this, we see both of the stuff that we've been talking about. We see that in the first case, the counter ion was positive and the complex ion was negative, while in the second one, the complex ion was positive and the counter ion was negative. So again, this illustrates what I was talking about earlier, that it is possible that the counter ion could be positive or negative, while the complex ion as well can be positive or negative. So it really is dependent on your oxidation states in your complex ion as to what you end up with. But again, you could have it either way. In terms of positive or negative, each of those things can be positive or negative. It is important, again, as I mentioned before, it's always just like normal, positive guy first and then negative. So positive counter ion, negative complex ion, or positive complex ion, negative counter ion. Now, to answer your question, I think how we knew the coordination number, I believe for the first one, when we're looking at the coordination number for either of these, but we'll look at the first one first. We have our gold, okay? And the gold is going to be in the middle. And each of our ligands in this case of the first guy was hydroxide, right? And hydroxide basically is that deal. So we basically have 4 hydroxides. One going in there. One down there. One there, and one more here. Okay. Now, the definition of coordination number is how many atoms are directly attached basically to the metal. Now, in hydroxide, the only atom in hydroxide, and we'll draw it out more like this so you can kind of see it, that can basically donate a pair of electrons is just the oxygen part, which means when they attach here, you basically have 1 atom attached directly, 2 atoms attached directly, 3 atoms attached directly, and 4 atoms attached directly, which gives you that coordination number of 4. I'll get that answer right now. So let me get to that question. We could kind of do it right here. So this right here technically would make up your complex ion part, right? So if you kind of put brackets around it, kind of like what you do if you drew a Lewis structure for an ionic compound. Remember that the gold here is +3. And in this case, each of these hydroxides are -1, which means overall this thing is a -1 charge like we saw here. Yeah. And just like in an ionic compound, the counter ion is not really attaching anywhere. It's attracted by the positive and negative attraction there. I'll just draw it that way, between the counter ion and the complex ion. So it's not directly attached to the gold or the hydroxide or anything like that. It's much like when you have sodium chloride, right? The sodium ion is like this. Chloride ion is like this. And there's no sharing of electrons or anything here, but they're attracted to each other based on the charges. And that's the exact same deal you got going on here with your counter ion and your complex ion in this case. Makes sense on that? Any questions on that? So again, you could really kind of think about sort of your coordination compounds as almost really like ionic compounds. Yeah, so coordination number really is just truly focused in on the complex ion, because that's unlike say the potassium and the entire complex ion, where there's no base sharing electrons. Here we are sharing electrons, really, right? We're donating a pair of electrons and kind of sharing, if you will. So they're going to be transferred in there. A little bit more of a sharing situation. I won't say perfectly sharing, really. They're kind of transferred, but you know, it's more of a sharing aspect inside the complex ions. So the coordination number is strictly just look at the complex ion part. Again, the counter ion really not doing much in sort of our application other than just there to balance out the charge, you know. So I almost want to like it to like a spectator ion, if you will. It's there, it's, you know, involved, it's in the solution, whatever it may be. But overall, it's not truly participating all that much in that sense. Other questions on that? And just to sort of relate it to the other one, if you look at NH3 and you draw NH3, it looks like this. And again, here with the chromium, you have the nitrogen coming in, you have another NH3, another NH3, another. I'm gonna run out of room, but we'll go one more here. Squeeze them in and squeeze in. Very badly squeezed in, but you got 1, 2, 3, 4, 5, and 6 nitrogens that are attaching to that chromium. Again, each of those nitrogens are monodentate, which means only the nitrogens directly attaching to that chromium. And again, here, you know, that's what would be the coordination number 6. Any questions on that? And in that same deal, although I drew it really badly there, not a lot of room, but this overall thing here would be positive, kind of like here. You would have all those nitrates, again, just attracted to it because of the negative charge, but not really directly attached to the complex ion. Again, just there really to balance out the charge. Other questions on that? Okay. So let's talk about how you name these guys. And this is the fun stuff. Not really, but we'll talk about it anyways. So these names can be fairly long when you get going on them. So let's talk about sort of the rules when we go to name these guys. Just like an ionic compound, as we've been talking about, the positive guy will come first and then the negative. So cation before anion. Again, that is both in formula and name. Within a complex ion, you always name all the ligands first in alphabetical order, regardless of prefix that there might be. You go actually with just the name of the ligand. And then the metal name always comes last. So this is an important thing to understand is the metal name always comes last. What that means is the metal does not always come last in the overall name. But when you're naming just the complex ion part, it will always come last. And in addition, we typically always include a Roman numeral with that metal when we name it. Now, some anion ligands will end with a slightly different name. So some of the ligands will not necessarily have the same name that we normally call it. So some of those guys that are negative will end with an O, and we'll see like a table in just a second of some of these. Some of the neutral guys are also named as they would be as their normal molecule, but some do have exceptions, like water is sometimes called aqua in some books, and some people will call it aqua as well, A or O. CO is carbonyl. NH3 is amine with 2 M's in it. Now, if you happen to have more than one of the same ligand attached, so like in the last two, we had multiple NH3s attached. We had multiple OH minuses attached. We do use prefixes for those to indicate how many of those ligands are there. So tri is 3, di is 2, tetra is 4, penta is 5, and hexa is 6. Now, some of the confusing things that occur as you go to name these guys, if a ligand contains a prefix in the name already, you then would use bis for 2 of them, tris for 3, tetrakis for 4. So what that means is if the name of the ligand itself actually has a prefix in it, you would use not di, tri, tetra, penta, or hexa. You would use bis, tris, or tetrakis if you have more. And the common one is that you come across a lot is that en that we saw earlier. That en which is known as ethyl endyl diamine. So in its actual name itself, it has that diamine part. And because it has that di part of it in its name, if you had more than one of them, you would then default to these prefixes here. And we'll sort of see that as we go along. Also, oxalate is sometimes, if you have more than one of those, people like to use the bis, the tris, the tetrakis for oxalate in terms of that. As I mentioned, the oxidation number for the metal is always given in Roman numerals. So almost like type 2 ionic compounds where you give the Roman numerals to indicate the charge on the metal, you do that always for the complex ion. And that includes some weird things that you also do with that you might not normally do in sort of normal nomenclature. So for example, something like silver, which has a +1 charge and is fixed. Normally when we name silver, we don't include the Roman numeral, but in complex ions, you actually do include the Roman numeral. So that's something that's slightly different. Same thing with perhaps zinc and those type of things. So even guys where we kind of normally would not include the Roman numeral when we're doing complex ions and stuff like that, we do include it. And an even weirder one is most people will actually include, it is possible to get a neutral metal. It can happen. And people will actually include, I guess it's not really a Roman numeral, but they'll include a 0 in parentheses as well. So there is a chance that all the ligands and the counter ions and all those good things will sort of cancel each other out. And oddly, the metal will have no charge. And again, I don't want to say Roman numeral 0, but they'll include sort of the 0 as well. Now, lastly here, the complex ion, if it is negative, so if it is negatively charged, just the complex ion part. So again, if we kind of go back real quick here, take a look at those ones we were kind of scribbling around here. When we look at each of these coordination compounds, we see that, as we talked about, the one on the left is a negative complex ion, and the one on the right is a positive complex ion. And by the way, you can know that by just looking at the formula here without actually doing any calculations. We see potassium comes first, which is positive. Complex ion comes second, it's negative. Here, the complex ion comes first, which we know is positive, and the counter ion comes second, which is negative in that particular case. Now, in the case of the first one here, if we get a complex ion that is negatively charged, when we go to name the metal, we actually will kick it old school, if you will. If you remember perhaps when you learned nomenclature, instead of Roman numerals, you could use more of those historical classical names for elements. So iron, for example, instead of iron, you could call it ferrate or ferrous, right? Copper, instead of obviously copper, you could call it cupric or cuprous instead of using the Roman numeral. So here in complex ions, if the complex ion part is negative, we actually do roll with the old school name. So we do roll with that old school name, and we don't use the name that is on the sort of the periodic table, if you will. Now, if the complex ion is positive, like was the case in the second example there, we would use the regular name of the element. So if we had something like iron, we would just call it iron. We wouldn't call it ferrate. So that's a lot of rules. We're going to look at some here and sort of see how we get to all of our names. But let's take a look at some of these tables and some of these names that we come across in terms of ligands and so forth. We have some neutral molecules. So like I said, H2O, some books will use aqua, some books will use aqua. I don't remember off the top of my head what way your book uses. I almost want to say aqua, but some books will also use aqua as well. Amine, we have CO as carbonyl. Our sort of halogens are named kind of like you might imagine, an almost organic way of naming them. So fluoride is fluoral, chloral, bromol, iodo for iodine, hydroxo for hydroxide, cyano for cyanide. And here's what I was talking about. Again, if our complex ion is negatively charged, we would roll with this sort of older way of naming the metal part of it. And here we could see, again, iron would be ferrate, copper would be cuprate, lead would be plumate, argentate, and so forth, stannate for tin. Here's another table, again, you can use for reference point as well, of some of our other ligands that you commonly, I'll spit that out, commonly come across. And here we have things like our bromol or chloral. Some of my other favorites here are nice carbonato over here. Or maybe I want an oxalato. I feel like I'm ordering a beverage at Starbucks here. So some of these guys have some different sort of names happening here. Here's our ethyl endyl diamine, which honestly, in terms of naming and in formulas, people do just roll with the EN usually. This is our EDTA here. Now, what I was talking about earlier in terms of those prefixes, like we use di, tri, tetra, unless we have a prefix in the name already, where we use bis or tetrakis, for example. Because of the name of this guy, this is what I was saying earlier, this ethyl endyl diamine has the di part of it in the actual name itself. Again, if you had more than one of those, that's a case where you would default into that bis or tris or tetrakis. Same thing with this guy. And although, doesn't necessarily write out, you see sort of a prefix in the name. People also will with this guy here, oxalate. They will use the more bis, tris, and tetrakis to indicate if you had more than one of those guys for him as well. So that's a common one that you come across. So let's just take a look at, for example, one of those ones that we were just looking at, just to kind of see how the name goes about. Let's take a look at those two that we kind of did the oxidation numbers for. Let me just try to pop them up here real quick. So let's take this guy here, the K, and our AuOH4. And we'll also take our other guy, which was our chromium here. So we're going to do CrNH3, and there was a 6, and our NO3 and 3. Okay, that looks good. All right, so let's kind of go through these names here together, just so you could kind of see how we put all those sort of rules together, along with all the weirdness that may occur here in terms of these names. All right, so first off, if you're not sure what these things are, you do want to maybe identify, what's your complex ion, what's your counter ion. Again, a reminder that your complex ion is usually found in those brackets. And just the arrangement of this automatically tells us that this is going to be our counter ion. This is going to be our complex ion. And from the arrangement of it, we see that the counter ion comes first, so we know it's positive. and the complex ion part comes second, so we know it's negative. So the way that we name counter ions, for example, is very simply just like we normally would. So, if you had something like NaCl, you would call this sodium chloride. We would use the whole name here if it came first, right? If we had something like this and this pretend here was our counter ion that came second, even though there's two of them, this would be still called calcium and just chloride, right? And this guy here would just be sodium, right? So kind of the same idea here when we name these coordination compounds. The counter ion just kind of is named like you would if it was in an ionic compound. So the first part of the name is pretty simple. It is potassium, right? So we're just going to use the whole name like we kind of would in an ionic compound. So now we got a couple of things happening here on our complex ion. We have our ligands, and we have 4 ligands. Prefix for 4 is tetra. And our ligand is OH, so hydroxide becomes hydroxo. So we would put that together. I'm just going to write it underneath so I don't run out of room. So this is going to be tetra hydroxo. Now, the important part here is when we look at the complex ion part, we already established that the complex ion part is negative. And if you remember this there of stuff that we were looking at, when the complex ion part is negative, where do we go? When the complex ion part is negative, that is when we use those old school ways of naming it. So when we look at this, which is gold, right, I believe, we want to use this name instead of gold. So we would use aurate. So coming back to our name here, this would then become aurate, right, instead of gold, because the complex ion is negative. And earlier we figured out that the oxidation state of the gold is 3, Roman numeral 3. So this is potassium tetrahydroxo aurate 3. Now, when we were talking about the Roman numeral and the complex ion part, as you can see here, I'm just going to underline it. This part of the name is all from the complex ion. And in the complex ion part, the ligands come first, the metal comes last in the name with its Roman numeral. So that's what it was talking about, that the metal part of the complex ion always comes last in the name. Question on that name, how we got there. It is kind of 2 names if you're wondering that. Is potassium spaced and then that big long name there for the second one. So let's take a look at the difference, though, if we look at the second one that we dealt with. And the second one that we dealt with, again, from the positioning here, we know that this is our complex ion. It's in the brackets. This is going to be our counter ion in this case. And since our complex ion comes first in the formula, we know that it is positively charged. And our counter ion comes second, which means it's negatively charged. Since the complex ion part here is positively charged, that means we could just use the regular name of the metal, which is chromium in this case. But we do want to start with the ligands. So here we have 6 ligands that are ammonia. Prefix for 6 is hexa, and ammonia becomes amine. So we would start with that. So that is hexaamine. And again here, the metal, which is chromium, we could just use chromium. The whole name, just like we would, again, because it is positive. We also figured out lastly in that example that it had a +3 charge. So Roman numeral here, 3. And now we come to our counter ion name. So just like I was talking about up here, that if we had Cl2, we wouldn't call it anything like dichloride or anything like that. We would just simply call it chloride. So here we're just going to use the name of the counterion, even though there's 3 of them. It has no effect on the name. And that counterion is nitrate. So this is hexammine chromium 3 nitrate. And what we see is the same thing it talked about. And again, just to point it out to you, what I'm underlining now, if I could find where I'm at, there it is. This is the complex ion part. And just like what we did above, we started with our ligands. We ended with the name of the metal and the Roman numeral. And in this particular case, because the complex ion was positive, the last part of the name is actually not the Roman numeral in the metal. It's actually the counterion. So when they talk about, again, the metal always comes last in the name, it doesn't mean last in the complete name of the coordination compound. It means last in the name of the complex ion part of the name. Any questions on that? As you can see, these names are long and can be very interesting. All right, let's see here. We're going to skip this one. I think we'll roll through this one. Why don't you try these 2 here? So take a couple of minutes here, and the first one we want the name. The second one there we want the actual formula. So see what you come up with, and then we'll talk about them. Let me see your question there. Okay, we'll go back. Let me ask those 2 questions before you get to these then, just to make sure here. Okay. So to answer, we'll start with the first one there. Is there any capillation spaces in that part of the hexammine chromium? There is no space or anything like that. The only space would be between, go back one more there. Oops, there is. The only space, come back, there you go. The only space would be between here, so I'll just put a circle. Yeah, between these names would be a space, not a dot, but that would be the space. But all that would be one sort of name together. So the hexammine chromium 3 would all be kind of one name. And then you would put a space and then the nitrate. Above there, potassium, then there would be a space. And then that tetrahydroxyurate 3 would all be kind of one name. So that answers, I think, hopefully that question. And then to answer your question on this one we skipped, we'll just kind of go over the name just to show you how they got to that name. Oops. And by the way, the formula here is kind of wrong. It actually should be, the dot should be up here, not down here. So it actually should be here, the dot. Because it's a hydrate, it's kind of a weird one. It's a hydrate. But to really answer your question is, this is our complex ion part. This is our counter ion. And again, this one's a little bit weirder because it's actually a hydrate with it. So if you remember, a hydrate is something that basically has water molecules that go with it. And basically, they're written with those little dots, right? Between the water part and sort of the salt part, if you will. You know, I just get that eraser out of here. So there's actually 2 sort of components going on in here. But if we just kind of focus in on this part of it, this coordination part, again, our counter ion is positive, which means our overall ion here is negative. And because it's negative, that is why this would be chromate. And in terms of charge, water is neutral. There's 3 of these potassiums, which gives you a +3. This is oxalate, which is -2. And there's 3 of them, gives you -6. So to balance it out, the chromium here would be +3 in terms of its oxidation state. And that's how they get to the chromate 3 part of it. The trihydrate comes from the water part, so that's just normally how you would name a hydrate. It's basically a prefix and hydrate to indicate how many waters, right? So the prefix indicates how many waters. Hydrate is what we use for water. Now, in this case, we have 3 of the oxalates. So as I mentioned previously, oxalate becomes oxalato, which is where the prefix name comes from. And as I also mentioned, this is one where sometimes people will use tris for this because there's 3 of them. And sometimes people will use tri for this one. Again, although it's not very obvious that this has a sort of prefix in it, some people kind of treat it that way and will use the tris rather than the tri. For us, you can use either one, but you will see definitely for our oxalate or oxalato there, you'll see it twice. And then our counter ion is just potassium to begin with. So that's how we get to that name, potassium for the counter ion. Tris oxalato for the 3 oxalates that are attached to the chromium. The chromium becomes chromate because the complex ion part is negative. And then the trihydrate is the 3 waters. And just to give you an idea, the counter ion is potassium. There's 3 of them. Our complex ion has an overall charge of -3 in this case. Yeah? So -3 and our +3s here balances out in that case. Yeah, so for oxalate, again, like I said, that's probably the most common one you'll come across where, people maybe do it both ways. But either one technically would be the IUPAC name. The IUPAC is the International Union of Pure and Applied Chemistry. They're like the guys that basically come up with all the names. It's chromate because, again, of that rule that if the complex ion part is negative, you use the old school name of naming it. So in this case, as you can see on the top right here, the complex ion part, the part in the parentheses, or the brackets, I guess is the better way to say it, the part in the brackets has an overall charge of -3. And whenever your complex ion part is negative, then you use the old way of naming it. It is only when your complex ion part is positive that you would use kind of like the regular name if you want to think about that. So if the complex ion was positive, then you would use chromium. But here, because the complex ion part is negative, you have to go with the kind of the older school name of a way of naming it. Questions on that? While we're here and we looked at this one, what would be the coordination number for this guy? So take a second and think about it before I tell you. What do you think the coordination number is for this? So the coordination number for this is, as it says right here, and see it actually said it, it is actually 6. And again, the important part here is what I was trying to get across earlier. It's not always going to be this number that I'm circling. And it's not this number because in this particular case, the ligand is oxalate. And as we saw earlier, oxalate, for every one of those oxalate molecules that are there, you actually get like 2 for the coordination number if you want to think about it that way. So since there's 3 total oxalates there, that is 2, 4, and 6 oxygens that are basically attaching to that chromium. And that's why, again, here the coordination number is going to be 6. So sometimes people fall into that trap where they just look at the little number on the bottom and assume that that's going to be the coordination number. And it will be if the ligand is monodentate. But if the ligand is not monodentate, like in this case, oxalate is actually bidentate, then, you will have to adjust the coordination number. Any questions on that? So this was a little bit kind of weird. It has a hydrate aspect to it. But if you want to kind of ignore the hydrate part of it, if we got rid of the hydrate part, this would be kind of like what we were talking about as well. You just got to cross that part out. Any questions on that? All right, so why don't you try a couple here that you got, and we'll talk about it. All right, So again, the first one, we're looking for the name. Second one, we're looking for the correct formula. So take a couple minutes and then we'll talk. Sorry, give it a second. Our complex ion part is coming first in the formula, so we know it's positive. Our counter ion here would be second, which we know is negative. Badly done, negative there. Negative, that's better. All right, so what we want to do then is start with our complex ion, and we do have 4 waters, so that's going to be tetra for 4, aqua or aqua, depending on your feeling. We also have 2 Cls, so that's going to be dichloral. So we want to put this together alphabetical. So alphabetical is actually going to be A before C. So we're going to put them in alphabetical order regardless of prefix. So this is going to be tetra, aqua, dichloral. Now we need to figure out a couple of things here. Water is 0. Chloride is -1, and there's 2 of them, gives us a -2. There's also a chloride on the outside that's -1. All that together tells us that the chromium here is +3 in terms of its oxidation state. And since the complex ion here is positive, we can use the regular name for chromium. We will use Roman numeral 3 to indicate the charge on the chromium. And now what's left is our counter ion, which we just named like normal, and that will become chloride. So that is tetra-aqua or aqua dichloryl chromium 3 chloride. Any questions on that name? Now, for the second one here, we are looking for the formula. So basically, we just want to put it together correctly. So let's just dissect the name here. Tris ethyl endyl diamine. Again, we're using tris because the name of the ligand itself has di in it. And basically, tris means 3. And for our formula, you could just use En if you like, or you can write out the formula. But most people just use En. And we have 3 of them, so that takes care of that part. Cobalt Roman numeral 2 means we have a Roman numeral 2. And since the metal here comes at the end of the complex ion part, we know that this part here is the complex ion part of the name, while this part here would have to be our counter ion. So again, remember that the metal with the Roman numeral comes at the end of the complex ion part. So that's how we know this is the complex ion part. So if we build that together, our CO and our En with a 3, if we look at the overall charge here of this complex ion, this is +2, this is 0. And that means that the complex ion part is +2. And it's really important to know that because our counter ion here is sulfate, which is actually -2 in this case. That means we actually just need 1 counter ion there to balance everything out. And it would look something like that. Any questions on any part of the name or how we got to that formula? Okay, so I think got a few more examples there. Why don't you give those a go, see what you come up with. And again, I'm not sure if I think they were corrected on your handout, but just in case, if they look a little different to the ones that are on the screen, but I think I got them corrected. So here we're looking for the name for each of these. So come up with the name and see what you end up with. By the way, before you get to those guys, let's just go back here just to make sure. In terms of coordination numbers here, the coordination number for this guy should be, what do you think? And what is the coordination number for this guy? So take a second there and figure out the coordination numbers, and we'll talk about it. All right, so here on the first one, we have 4 waters and 2 CLs attached. Both CL and water are monodentate, which means the coordination number here would be 6. On the bottom, coordination number would be 6 as well. So remember that this En is bidentate, which means for every one of those, it will attach in 2 places, and that will give you a coordination number of 6. So again, as we were talking about earlier, not always going to be this number in terms of the coordination number. So actually, both of these guys happens to be a coordination number of 6. All right, now back to the other ones there. All right, so come up with the names for each of these guys. Take a couple minutes and we'll talk about it. Okay, so let's take a look and see how we're doing. So starting up here, a couple things you do want to figure out, obviously, is some oxidation states. So our NH3 is 0, our Cl is -1, Cl here is -1, but there's two of them. That gives us a -1 and a -1, which is -3. So to balance it out here, our cobalt will be +3 in this case. We also see that our complex ion part comes first and it's positive, followed by our counter ion, which is negative, right? How did I get 6 for the coordination number? Let's take a look. I'm assuming you're talking about perhaps the bottom one. Is that's the one you're talking about? So for the bottom one, which I'm assuming is the one you're talking about, it has to do with the ligand. So the En ligand is the one that looks like this. And for every one of those ligands at En, at this nitrogen and at the nitrogen on the left, in each of those En molecules, it can bind in 2 different places per molecule. So when we have 3 total of those guys, those En molecules there, each one could attach in 2 places. And again, 2 times the 3 gives us a grand total of 6 for the coordination number. Again, because it's a bidentate ligand. And that's how we get to 6. As opposed to the one on top there where water will only attach through the oxygen. And there's 4 of them. So that gives you 4 oxygens that are attached. And the Cl in the top one, there's 2 of those. So we can only attach through the Cl. Because both of those are monodentate, we could just add up the numbers on the bottom, the 4 and the 2. And that gets us to 6 for that guy. Because each of those are only attaching in one place per molecule. You're welcome. All right, so coming back here to our name, I think. So since our complex ions is positive, we can use the regular name for it, which is cobalt. So we definitely have cobalt 3 for the charge. We have 5 of these ammonias. So 5 is penta, and ammonia becomes amine. We also have 1 Cl, which is chloral. We want to put this in alphabetical order for our complex ion part. So A before C. So we're going to go with penta, amine, chloral. And again, the complex ion, the metal comes last. 3. And now we have our counter ion that's left. And again, even though we have 2, we're just going to name it like normal. And this would become chloride. So pentamine chloral, cobalt 3, chloride in that case. Any questions on that name? Sorry, I'll some things here. So I think that should be okay. So your question is the number in the counter ion wouldn't appear in it. Yeah, so if you're asking about the number here, even though there's two of them, we would just kind of name it kind of like a normal ionic compound. So that's what I was talking about earlier, the CaCl2. We would call this calcium chloride, right? Even though there's a 2 here, right? It has no effect on sort of that name. And it's kind of the same thing here. We wouldn't call it obviously calcium dichloride or anything like that. So even though there's more than one, the counter ions are pretty much just named like normal. So if it's a metal at the upfront part, you just call it whatever it is, just like normal, no prefix or anything like that. If it's a negative counter ion, you just use IDE at the end of it, or if it's a polyatomic ion, you use the whole name of the polyatomic ion. So looking at our counter ion here in the second one, it is K, so we would just call it potassium. And here we have 6 of our prefixes here, which is hexa, cyano for our cyanide. And here again, the complex ion is negative. So we're going to use the older way of naming it, which is going to be ferrate. We're also going to include the Roman numeral here, which is 3. So this is going to be potassium hexocyanoferrate 3. Question on that name there. Now, for example, let's say we had just this. And we wanted to name just this guy, right? So that basically is not a coordination compound. That is just a complex ion. But you would name it the exact same way. The only difference is you don't include the counter ion part, right? Since it doesn't have it. So this guy, if we had to name just the ion by itself, you would call it, this is the hexacyanoferrate 3, and you would perhaps put ion at the end of it. And same thing on the one above. If we took the one above and just the complex ion part, which would be this part of it, this would be just the front part of the name, the pentaamine chloral cobalt 3 ion. So if you don't have a coordination compound with that counter ion present, you can name the ions the exact same way, and you just put ion at the end of it. Any question on that there? Okay. So we did a couple of names. So why don't you try a couple of formulas here, where we finished talking about naming and all that good stuff. So take a couple of minutes and write the formulas for each of these. Okay, so let's take a look here. So again, we want to write some formulas here. So when you have the name, you really just want to kind of put the pieces together. Let's go with orange. Haven't done that in a while. All right, so let's just take the pieces apart here. By the way, we can identify really this part of it as our complex ion part. And we know that because, again, the metal name always will be at the end of that complex ion part. That means that this guy here is going to be our counter ion. So taking this apart, we got triamine. So amine is NH3. Tri is 3. So that takes care of that part of it. Bromo is bromine, right? Basically. And we just have one of those. So that takes care of that part. Platinum 2 means we have a platinum with a +2 charge. So we want to put these guys together. And again, in our complex ion part, we could do that. We could do a little bit of that there. And we got one of those guys. And now basically putting it together and thinking about all the charges we got going on, we can figure out the overall charge of the complex ion. This is going to be +2. That's going to be 0. That's going to be a -1. That's a lot of math there, but I'm going to go with +1 in terms of the overall charge there for our complex ion. Now our counter ion, which is chloride, is Cl-. So again, it's important to figure out the charge on your complex ion because that will tell you how many counter ions you need. And in this particular case, we actually have a +1 and a -1 here. And that means when we put it together, we only need one of each. So that would get us something that looks like this. Any question on that one there? Now, if we look at the second one, again, we could recognize that this part is our complex ion part as the metal comes last here. This then would be our counter ion. So again, just dissecting it, potassium is going to be K+ as our counter ion. Hexafluoral, that means I have 6 of these fluorines, right? That's what hexa means. Cobaltate is going to be cobalt with a +3 charge from the Roman numeral there. So that is my complex ion part. Looks something like this. Again, each of these are -1, and that's -6, which means overall my complex ion is going to have a -3 charge. And again, that's important because when we now come back to our counter ion, we don't need 1, we don't need 2, but we actually need 3 of these guys, right? To give us +1, +2, and +3 to balance it out. So that means putting that together, K3COF6 would be our formula here. Any questions on any of those formulas? Now, while we're here, let's talk a little bit about coordination number. Coordination number on this guy is going to be 3 and 1. That's going to be a coordination number of 4 in that particular case. Coordination number down here is going to be 6. And in this particular case, again, each of those guys are monodentate, which means you can actually just use the little numbers on the bottom and add them together because they only bind one place per molecule or ion. Any questions on how to name these guys, how to write the formulas for these guys, or anything like that? Okay. It's probably enough torture, I suppose, for today. Yes. Let's talk about a couple of things here before we call it a day, I think. The The next exam is 1 week from today, which is Thursday. And I think that's May 28th, if I'm not mistaken. It will cover chapter 16, which, if my memory serves me correctly, should be thermodynamics. It will cover chapter 17, which is the electrochemistry chapter. And it will cover chapter 19 up until here. Yes. So exam, I guess that is 3 since we're getting to the end, right? All of chapter 16, all of 17, and chapter 19 up to here. And again, that should be May 28th, right, is when we should be taking that. Any questions on the badly written stuff there? Any questions on the exam and what it's going to cover? So there's just a few little things left in this chapter. We'll talk about, I think, on Tuesday. Again, like I said, I think I put you through enough of me lecturing to you. Probably don't want to listen to me another 3 hours or so. So we'll go with all of chapter 16, all of 17, and whatever we covered up through here today. And again, that should give you a week to kind of study all that good stuff. I'll be truthfully honest with you. The chapter 19 homework will consist of the entire chapter, to be honest with you. We usually finish chapter 19 before we take the exam. But again, we had some of those weeks off and stuff like that. So what I'll do for chapter 19 homework then is I won't officially make it due next week with the exam. So for the homework, for the exam 3, you could turn in, if you want, 16 and 17. You could hold on to 19 and give it to me a little bit later if you want. Again, since it will cover content from chapter 19, I would probably do the ones that you could do. And again, by Tuesday of next week, you'll be able to do them all. But if you want some extra time and not have to turn it in, you could hold on to 19. But again, obviously content will be on the exam from 19 up through this point. I just don't know off the top of my head how many are questions from what's left of what we're going to talk about. Probably a majority of the homework would be probably what we've already talked about. Hang on, let me take a look and see. No, so out of 19, in terms of the content from chapter 19, it will be just up until pretty much the slides. So everything's fair game from chapter 19, from what we talked about here in lab at the beginning of this chapter to this slide right here. Anything that's past this slide will not appear on next week's exam, okay? It will appear on the final, but it won't appear on next week's exam. So that's why I say, in terms of the chapter 19 homework, I would recommend doing it. I think you probably could do 90-ish%, if not more, at this point if you wanted to. But since technically the rest of 19's homework won't be on this next exam, if you need a little bit more time, you could give it to me a little bit later. But definitely chapter 19 will be, on there in this content up until this slide. Yeah, I believe exam 2 grades are already posted, if I'm not mistaken. I hope so. I seem to remember grading them. I thought I posted them. I'll double check, but they should be, I believe, up there, if I'm not mistaken. But I'll double check. It's been graded. I thought I posted them, but I'll take a look and just to make sure that sometimes Canvas is weird. It doesn't post it correctly. But they should be up there. Yeah, they've been graded, I think, already. So I'll double check when we're done here and make sure that they're up there. If not, they will be up there very shortly, but they should be up there, I think. Other questions on that? And I apologize if they didn't get posted. They should have been already. All right, so the exam, like I said, will be 1 week from today. again covering chapters 16, 17, and 19 up until this slide. So nothing. So basically, what's left is there's isomers that we're going to talk about, and there is weak field, strong field, and ligands, and sort of all that type of stuff. So that stuff we'll save for the final, but up until here. In terms of labs, like I said, what you got out there, I think today is titration due. Again, make sure those get in. I believe, again, the submission is set up in a way if for some reason you weren't able to get it in on time by the due date. I think you could still submit it. It'll just be marked late. And then obviously I'll take into account the appropriateness of any deductions based on how late it is. But I think it should still be open for submissions. If by some chance you don't have it done, I hope you do. If not, you should spend the rest of the time, doing that. But you could still submit it. And then you have the redox reaction or experiment that's up there. And today or by tomorrow, I'm going to post the next one, which is electrochemistry. And let's just talk about that experiment really quickly. I think it should be pretty self-explanatory, the one that's going to go up, which is the electrochemistry experiment, which technically was on the schedule for today and Tuesday, I believe. And basically, in the first part, I think part one, you're going to build some different galvanic cells, or they built some different galvanic cells. And they basically put some electrodes in it and got the voltage for those cells. So there'll be, I think, some pictures of the cells, what they look like, and then the cell voltage that you have to read. And you're going to have to calculate some things using the formula that we've used a lot at this point. E of the cell is E of our cathode minus E of our anode. It may actually ask you to write the anode equation, I think, our reaction, the cathode. You're going to have to do some of those things, I think. So I think mainly part one is pretty much that. It's again, should be pretty self-explanatory based on our lecture and even, what we've been talking about. You're just going to build some different galvanic cells. You're going to use those SRP values maybe to write up the reactions and calculations and figure out perhaps the theoretical and then also versus the experimental values that they got. So I believe that's part one of the experiment. Like I said, I don't think it's super difficult in terms of material. It's a lot of what we've been talking about, definitely in chapter 17, and even a little bit there in sort of that redox experiment. Part two, they're also going to do kind of the same deal. They're going to build some galvanic cells. But if I remember correctly, they may build what are sometimes referred to as concentration cells. And what a concentration cell is, so normally, right, if we build a traditional galvanic cell, right, we have our anode side, we have our cathode side, right? And perhaps say this is zinc over here, right? And say this is, I don't know, copper or something like that. And we usually build it out of sort of two different elements, if you will. In a concentration cell, we would sometimes build a cell out of like the same elements on both sides. So for example, I'm just go with I2, I think iodine or something is what they use in one of them. So in this case, the anode and the cathode are both really the same elements. And this is why it's called sometimes a concentration cell, because they're both the same element. You're like, well, how could one be the anode? How can one be the cathode? But there is a difference in terms of each of those sides. One side has a certain molarity. The other side has a different molarity. So here in a concentration cell, it's the difference in the molarity that basically will cause the difference that's needed to allow those electrons to go from one side, to the next, right, as it travels. And so I believe in part two, they built some concentration type cells like that. So you'll see basically the same half reaction on both sides. And basically what that means under standard conditions, which means they both would all have the same concentration, 1 molar each, right? Under standard conditions, and again, I'm just going to make up the numbers. I don't know iodines off the top of my head. Let's just say it's 4 volts. It definitely is not 4 volts. So just a number I randomly just made up. So if you did this, right, and if they all had the same concentration, you would do your cathode minus your anode, which would technically give you a cell voltage of 0. But what you're going to be doing is using different concentrations of each of those, where they're both maybe not 1 molar. And if they're both not 1 molar, that should get you to think about a certain equation that we saw when we were talking about sort of E of the cell and so forth. And that is when we deal with non-standard conditions, and that's our Nernst equation. So if you remember our Nernst equation, E is equal to E naught minus RT NF natural log of Q. So if I'm not mistaken, I believe in part 2 of the experiment, when you built sort of these concentration cells and the concentrations aren't 1 molar, you are going to need to use the Nernst equation to figure out the cell voltage. So again, that's going to be your products, right, over your reactants for Q. The R is our 8.314, our temperature in Kelvin, Faraday is a constant, our moles, and our E of the cell under normal conditions, which in this particular case, if they're the same on both sides, this guy's going to end up being 0, right? Which will kind of get you to, you know, this type of deal, right? So you will have to use the Nernst equation in some of these calculations, and I believe in part 2 you'll need to use that. So remember, you want to use that Nernst equation whenever things are not in standard conditions. So that means, again, concentrations are not 1 molar. If it has to do with anything with gases, which I don't think is in an experiment, they're not 1 atmosphere and so forth. Any questions on sort of the experiment that's coming up? Again, should be pretty, I think, self-explanatory. And I apologize, I don't remember what part 3 is off the top of my head. And but I think maybe part 3, if we do part 3, I'll have to look at it. Is very similar to part 1 and part 2 sort of situation. You may have to use the Nernst equation. I think in part 3, they build this also a concentration cell. I think in part 3, I'm trying to remember off the top of my head. I want to say they build a copper concentration cell. And maybe part 2 is not necessarily a concentration cell in all of them, but they build sort of a copper concentration cell. And what they do is they make a complex ion by adding ammonia to it. So you have basically copper on both sides, on your anode side, your cathode side. And then I believe to one of the sides, they add ammonia to it. And by adding ammonia is, again, a strong ligand. Is going to want to make that complex ion. So I think in part 3, it's sort of a concentration cell where you then treat one of the sides, the anode or the cathode, with some ammonia. You're going to form a complex ion between copper, I think, and the ammonia. And you're going to be able, I think, if I remember off the top of my head, and I apologize, I could be wrong, but I think you're going to calculate something like the Kf for it, like the formation constant that we talked about in chapter 15, I guess it was. And you're going to do that by adding ammonia. So I'll have to double check part 3, but I think that's what's happening there in part 3. Any questions on that? So what I'm going to probably do is post that sometime either today or tomorrow, so you could get a shot at working on it. It will not be due next week or anything like that. But again, if you kind of want to work on that, you can. And then I think that should cover most of everything that's coming up. So again, a reminder, next Thursday, we will take the exam, 16, 17, and 19 through the previous slide. You have, I think, next week due the redox experiment. I will post the electrochemistry experiment the next day or so. And now that we sort of talked about it as well, and you could get started on that. It'll probably be due not next week, but probably sometime the following week. It also will be just kind of a fill in the data analysis and answer the post lab questions, pre lab questions. No type report for that one either. You'll just submit those things. And then I believe coming up, not next week, but the following week, that should be, I think, your presentations on your projects and all that. So again, make sure that you are keeping up with that as well. And again, if you have any questions on that, you can email me in regards to your project. If anything should have changed, group members or anything like that, just let me know. Any questions on anything coming up? And then the final happens at some point. I want to say like the 12th maybe or something like that. Any questions on anything? Okay. So I think we're just going to call it a day for now, I think. And if you do have any questions, feel free to email me or anything like that. Since I tortured you for almost a couple hours of lecturing, I think we'll just wrap it for today if that's good with everybody. And if you do have questions on anything, just feel free to email me and I'll be happy to get back to you. Other than that, have a good weekend and I'll see everybody on Tuesday.